Well, good morning, everyone. Happy Friday. And today's payday, too, so I'm real excited. Today I wanted to talk about gravity, and somehow I got off on atmospheric pressure. So, this is about atmospheric pressure, and I'm going to ask you a question. Do we need a container to hold the atmosphere? Raise your hand if you know the answer. Let's see. Do I see anybody? I need one of those magnifying glasses and I can say, there's Bobby and there's Timmy. You guys aren't old enough to remember that. This week's joke. You know what they say about cliffhangers? So my introduction, gravity is a force which tries to pull two objects toward each other. Anything which has mass also has a gravitational pull. The more massive an object is, the stronger its gravitational pull. The Earth's gravity is what keeps you on the ground and what causes objects to fall. Um, Obviously, we know that the Earth's gravity is much, much stronger than the gravity between me and you, or um, the gravity between a butterfly and the Earth. Um, so we'll talk about that some more. I like this cartoon that says, I'm not deploying my parachute until scientists get more certain about this gravity stuff. So let's get into pressure. Uh, and I'm going to talk more about this pressure. So there's some more coming about this too. For our purposes, there are three types of pressure. Atmospheric pressure, which we'll cover today. The atmosphere is a fluid. It's called a fluid. Any gaseous body is called a fluid, but it's compressible. The second one is hydrostatic pressure. Uh, this is the oceans, the lakes, seas, whatever. Water is also a fluid, and it's a liquid. Liquid is a state of matter. Liquids are uncompressible. And the last one is lithostatic pressure, which is the pressure from solid ground. Uh, and I hope you'll find this one very interesting when we get to it. Solids are uncompressible as a rule. So here's an equation for pressure. Pressure, let me define some variables. P, capital P stands for pressure. Rho is density. G is the acceleration due to gravity, which we all know 9.80 meters per second squared. H is the height of a column of gas or fluid, and S is time in seconds. So over to the right here, we see that pressure is equal to density times the acceleration due to gravity times the height of the column of gas or fluid. This is used for barometric meters that measure barometric pressure. Um, Another equation we can think about is this one down here, pressure is equal to force divided by area. So we have newtons. Pressure can be newtons per square meter. It can, if you use the foot-pound-second system, archaic, which the US uses, the units are pounds per square inch, or PSI. Newtons per meter squared can also be defined as a Pascal, PA, which is equal to 1 Newton per meter squared. Often you'll see kPa, which of course means thousands of pascals, just because of the magnitude of the numbers. So atmospheric pressure doesn't actually vary with height in a simple way, since the composition of the atmosphere is different at different altitudes. The pressure depends on local temperature, and the temperature depends on the amount of greenhouse gases and water vapor. So it varies. However, the general feature is that atmospheric pressure does decrease with height, and this is due to the Earth's gravity. So we all know, you hear stories about Mount Everest and people that climb to the top, and they need oxygen because the atmospheric pressure is so low. The people that live at Machu Picchu in South America, they also have to become adapted to very, very low pressures. If you go all the way to the exosphere, at the very top of the atmosphere, pressure is pretty much zero. So you can't really think of it as a sealed container, though, since the atmosphere is free to lose and gain particles to and from space. Were it not for gravity, all of the atmosphere would just fly off into space, which we are so thankful it doesn't. Here's some analytics. Don't know about you, but I like numbers. This graph shows atmospheric pressure versus altitude. Over to the left, the altitude is 0, so this is at the Earth's surface. And of course, atmospheric pressure is in kPa. At the Earth's surface, it's about 100 kPa. And then it decreases as we go up in altitude. At 10,000 feet, it's about 20 kPa. And then as you go up from there, it gets closer and closer to 0. If you know about graphing, you can see that that curve is asymptotic to 0. So at the highest values, it's 0. This little picture here shows air molecules are closely spaced at the bottom of the atmosphere and widely spaced at the top of the atmosphere. So gravity is holding down as much as it can, and then there are forces that cause the air molecules to increase in height, but they decrease in pressure. So when you think about flat earth people will not admit that we have a graduated air pressure, even though they will admit, that Mount Everest has a lower air pressure than sea level. But in any case, this second law of thermodynamics, again, which we hear constantly from flat earth people, that the globe contradicts the second law of thermodynamics, which is not true. It says that in a totally enclosed system, a gas will expand to fill a container. And here you have an example. You have one gas on the left, a different gas on the right, and they have a partition between them. You remove the partition and they expand to fill the container, and they wind up all mixed together. Now notice that if the gas doesn't expand to fill the container, you're contradicting the second law of thermodynamics. So in our atmosphere, which is a totally enclosed system, this means inherently that the gaseous air must expand to fill the entire enclosure. There could not, would not, must not ever be the gradient that we see in the natural world. If you had a totally enclosed system, so you think about this ridiculous dome and that the atmosphere is all enclosed and the gases must expand to fill the enclosure, that just can't happen in the atmosphere. The gradient that we see, as shown in this picture, the gradient that we see could not happen in an enclosed system. In the real world, there is not an atmospheric pressure next to a vacuum. You keep hearing this again, how can you have a pressure next to a vacuum? Well, as it turns out, the atmosphere decreases to 0 kPa at the highest altitude, which is by definition a vacuum of space. So the atmosphere starts at 100 kPa and decreases as the altitude increases until it's 0 kPa. So what we've done is the atmosphere just decreases until there's a vacuum. And I thought I'd tell you, just so you know, we do lose about 90 tons of material to space every day. Another thing about pressure containment that I always hear and just chaps my butt is about NASA and the comparison between the large vacuum chamber and the EVA spacesuit. So I looked at those two things. The large vacuum chamber at the Glenn Space Center is designed to keep pressure forces out. There are other forces besides air pressure. There are other forces such as gravity, architectural design, material design, and so forth. Think of this as like the ancients built Notre Dame, other cathedrals like that, and they have walls that are, very, very thick, and it's totally because of the design. They don't want it to fall. So, here we have this design, and the walls are rigid. One tiny leak could cause disastrous effects. And you remember the old story about the kid with his finger in the hole in the dike? Just one small leak. Total atmospheric pressure, just that part on the dome or on the vacuum chamber, is 55 million pounds, 14.7 psi, pressing in and down all the time. So yes, the walls do have to be very thick and reinforced with rebar because they don't want it to collapse. So that's that. The EVA spacesuit, on the other hand, is designed to keep air pressure in. When you're in space, the pressure outside of your spacesuit is pretty much zero. Where did I hear 1 times 10 to the minus 17 torr? And so they're trying to keep air pressure in. It's about 13 to 14 psi. They try to keep the air pressure a little bit lower than sea level. Notice that the spacesuit is very pliable. Your arms move, your legs move, the chest parts move when you move your chest. If you do happen to get a small leak, that leak can be repaired inside the ISS or whatever. But in the meantime, before it's repaired, the air pumps inside the suit maintain its pressure. The zipper that I keep seeing people show, how can the zipper keep the pressure in? And the zipper is on the outside of the EVA. There is other protection on the inside of the zipper. And I just get tired of people saying, how come we have to have this big vacuum chamber and the spacesuit is able to hold out air pressure? So my question at the beginning, you all raised your hands. Does a gas need to be contained? So let's suppose, just imagine that you have a pressurized box or enclosure and you open the lid. So there are 3 possibilities. If the box has more pressure than the surroundings, you open the lid and gas rushes out. You open the box and it has the same pressure as the surrounding atmosphere. Nothing happens. No, absolutely nothing. The box just opens. If it has less pressure than the surroundings, gas from the outside rushes into the container. I did notice in my research that if a box contains a heavy gas, such as sodium hexafluoride, that gas will gradually escape leaving a gradient pressure in the box. So there is a lot of the heavy gas at the bottom. The gas gradually escapes. So I thought that was an interesting thought. I also found the ideal gas law, which I knew about a long time ago. PV equals nRT. I used to have that memorized. PV equals nRT. P is pressure, like before. V is volume, and that's equal to N, the number of moles of gas. R is an ideal gas constant, has some value, and T is the temperature in Kelvin. And so this is the ideal gas law. So let's think about our enclosure for a minute. Volume V, because of being in a fixed enclosure, is a constant. The number of moles are constant because we've put some gas in there and it's going to stay. And so if we do a little arranging of our formula here, we get P, pressure, divided by temperature, is a constant. You can think of NR divided by V as just some constant. This means, think about it now, this means that for every change in temperature, there has to be a corresponding but inverse change in pressure. Here where I'm at, temperature varies from 265 Kelvin to 303 Kelvin. Sounds really hot, but remember that 273 Kelvin is 0. If the Earth were flat and enclosed, being that we have that temperature, the atmospheric pressure would vary from 100 kilopascal, which we remember, to 114 kilopascal. Again, that doesn't sound much, but that's 14,000 Pascal. There's quite a variation of pressure here. We don't see that. I don't believe in this case you could see that much pressure change. And really, the temperature here doesn't vary that much. You think of other places in the world, the Sahara Desert or somewhere like that, where it gets very hot during the day and cools way down at night. You could see how the pressure must change if we were in an enclosed atmosphere. So my conclusion for this is gravity holds the atmosphere down. You can clearly see that the pressure is higher at the ground level and decreases as altitude increases. And we're going to talk a lot more about this caused by gravity. So I hope you will stay tuned for the next installment of this. And it's really good to have you. I'm glad you guys tune in. I love seeing you every week. I read every one of your comments. Thanks for being here.